Welcome back to Math 107 College Algebra. In this video, we're going to take a look at systems of equations in 2 and 3 variables. And then these could be extended to any number of variables. So first, we have a system of equations. X plus 2y plus 3z. Whoops. We're doing two variables first, so I don't want a 3z. Equals 3. And 4x plus 5y is equal to 6. So there's two different ways I can solve this. The first is going to be the substitution method. So here, I'm going to solve this first equation for x. So I get x is equal to negative 2y plus 3. So now I can plug that in for x in the other equation. So 4 times negative 2y plus 3 plus 5y is equal to 6. So now I can simplify that by distributing the 4, so I get negative 8y plus 12 plus 5y is equal to 6. Combining like terms, I get negative 3y plus 12 is equal to 6. Now subtract 12 from both sides. And then divide both sides by negative 3. I get y is equal to 2. Now once I get that y, I need to plug it into the other equation. So I get negative 2 times 2 plus 3 for x. And simplifying that, I get x equals negative 1. And we'll usually write that as an ordered pair. 1, or negative 1, 2. So, that's one way to do it. We also could have done it so we have the same system of equations here. And this time, we're going to solve it using the elimination method. So what I'm going to do is I'm going to multiply both sides of that first equation by negative 4. And when I do that, I get negative 4x minus 8y is equal to negative 12. Then 4x plus 5y is equal to 6. And now what I'm going to do is I'm going to add both of these equations together, adding the left side to the left side and the right side to the right side. And I'm left with negative 3y is equal to negative 6. And now I can divide both sides by negative 3 and get y equals 2. And if I were to plug that back in to one of the original equations, I would find that x equals negative 1. So that's known as the elimination method. The first method was known as the substitution method. So when I have a system of two linear equations in two variables, there's three possible things that could happen. So this one, if I were to graph it, it would look something like that, where they have a single point at which they intersect. Now there's two other situations that I could have. One is the lines are parallel, and the other one is that, and that's not a good picture, I'm just trying to draw the lines right on top of each other. So they're actually the same line. So just looking at what that looks like with the elimination method. So first I have x plus y equals 1. I'll go ahead and do negative x minus y is equal to 1. So I add those together. I have nothing left on the left side. And I get a 2 on the right-hand side. So we get 0 equals 2. That's clearly not true. So that's going to be no solution. But the other possibility we could have is x plus y equals 1. And negative x minus y equals negative 1. I add those together, I get 0 equals 0. Now, that's a true statement. So we end up getting, the way this will be written in a lot of places, is the ordered pair xy such that x plus y equals 1. However, the way our book does it is we're going to go ahead and solve that first equation for y. So we get y equals negative x plus 1. And then we'll write our solution as x negative x plus 1 in that ordered pair format. So that's how we do things in two variables, and if we use substitution, we'd get something like that. With the parallel line solution, we'd get two things being equal that clearly are not. And in the same line situation, we'd get two things that are uniformly equal. We might get something there like 4 equals 4. Now with three variables, let me get my problem here. So you might have a system like 7x plus 5y minus 3z is equal to 16. 3x minus 5y plus 2z is equal to negative 8. And 5x plus 3y minus 7z is equal to 0. So, we could work a system with three equations and three variables using the substitution method, but that can be very tedious, so we're not going to do it. So the idea here is we're going to add two equations together, but we need to keep one of the original equations, and then one of the equations will get replaced by the sum. So I'm going to add the first two, keeping the first one, and then the second one is just going to be the sum. So I still have 7x plus 5y minus 3z is equal to 16. Now, adding the first two together, I have there we go. 10x. The 5y's cancel out. And I have a minus z is equal to 8. And then finally, with the last equation, I have 5x plus 3y minus 7z is equal to 0. So now I need to eliminate that y from another one of the equations. So if I multiply the first equation, both sides, by -3, and the third equation by 5, so I now have -21x minus 15y plus 9z is equal to -48. Still have 10x minus z is equal to +8. And now, multiplying the third equation by 5, I get 25x plus 15y minus 35z is equal to 0. So now I'm going to add the first equation to the third equation, and I'll go ahead and keep the first equation there. So minus 21x minus 15y plus 9z equals -48. And I still have 10x minus z is equal to 8. Then finally 4x minus 26z is equal to, let's see, that would be -48. So I've eliminated y from 2 of the 3 equations. Now I need to eliminate a variable from one of the bottom 2 equations, and the easiest thing for me to do here is to multiply the second equation by -26. So I'll do that. Minus 21x minus 15y plus 9z equals -48. That stays. Now multiplying the second equation by -26, so I get -260x plus 26z is equal to whatever 8 times -26 is. It's going to be -208. And then down here I have 4x minus 26z is equal to -48. So now I'm going to add those last 2 equations together. I'm going to put my answer to it in the slot for the third equation. So I still have -21x minus 15y plus 9z equals -48. Then I have -260x plus 26z is equal to -208. And now, adding those together, I get -256x is equal to -256. And now, I have some common terms in these equations, so I can get rid of those. So in the first equation, I have a common factor of, we'll call it -3, so I can go back to 7x plus 5y minus 3z equals 16. In the second equation, I have the common factor of, we'll call it -26, so I can go back to 10x minus z is equal to 8. In the bottom equation, I have the common factor of negative 256, so I can just go to x equals 1. Well, now we know that x equals 1. And now the second equation just has x and z, so it becomes 10 times 1 minus z equals 8. So I subtract 10 from both sides. I get negative z equals negative 2. Dividing by the negative 1, I get z equals 2. And now I can plug both x and z into the first equation. So I get 7 times 1 plus 5y minus 3 times 2 equals 16. Putting that all together, I get 7 plus 5y minus 6 is equal to 16. Combining my like terms, it's 5y plus 1 is equal to 16. 5y equals 15. And y equals 3. So putting that in the ordered tuple we usually do, that's going to be 1, 3, 2. And just like we had with the two-variable case, we could have different cases going on. There's too many for me to state explicitly, because of the fact that these are planes intersecting rather than just lines. We could have situations where we have infinitely many solutions, and we could have situations that we have no solution. So we'll talk about that some in class on Tuesday, along with a way that we can simplify the work that we're doing with these systems of equations. So I will see you in class on Tuesday.